Our goal is to maximize the function h of x equals x e to the negative ax over the interval from 0 to 2 over a, where a is greater than 0. So we have a situation where we have a parameter a in here that's going to move around our optimal point, but we can still analyze it using derivatives. So first thing we'll do is we'll take our derivative, which is going to be a product rule. We see our product right there. So we leave the x alone times the derivative of e to the negative ax, which is e to the negative ax, times the derivative of the exponent, which is negative a, plus now we leave e to the negative ax alone times the derivative of x, which is 1. And now we'd like to see how much we can simplify this. Well, notice we have a common factor of e to the negative ax. So let's pull that out. So we have e to the negative ax, and what are we left with? So this first term is negative a times x, these two, and then plus 1. So there is our first derivative, and this will allow us to find a critical point, and we do that by setting our first derivative to 0. This part here can never equal 0, so we'll just set negative ax plus 1 equal to 0, and we'll solve this. So we have 1 equals a times x, and solving for x, we get that x equals 1 over a. That is our critical point. Now, because we're on a closed bounded interval, max and min either have to occur at the critical point or the endpoints, and we're guaranteed of this. So we're just going to plug all these into the original function. So h of 0, h of 1 over a for our critical point, and h of 2 over a for their other endpoint. So h of 0 gives us 0 times e to the negative a times 0. Well, 0 times that is going to be 0. H of 1 over a gives us 1 over a times e to the negative a times 1 over a. Negative a times 1 over a, that's going to be negative a over a, or negative 1. So we end up with 1 over a e to the negative 1, or 1 over a times e. And this one's going to look really similar. 2 over a times e to the negative a times 2 over a equals 2 over a. Again, those a's will basically cancel, and now we get e to the negative 2, which is 1 over a times e squared. Now, excuse me, not 1 over, 2 over. Forgot this 2 right here. So the question is, which of these two is larger? Clearly, a is positive, so these are going to be both positive numbers. So we already know our min is 0, and it happens at x equals 0. So we want to see which one's bigger, 1 over a to the e or 2 over ae squared. Let's assume 1 over ae is bigger than 2 over ae squared. That e squared looks like it might change this. And what we'll do is we'll see if we get a true statement. So we can actually multiply both sides by e squared and by a. And what that does, that cancels this, cancels this, cancels this, cancels this. The a's will cancel, and we'll cancel out one of the e's, and we get left with e greater than 2, which is a true statement. So our max is right here at 1 over ae. Now, let's make sense of this graphically and see what's going on. So let's take a look at the graph. And what we can see is when a equals 1, we can see we have a max right there at about 1. X equals 1, excuse me, which makes sense because if a is 1, we have 1 over 1. And watch what happens as we move a. So the bigger a gets, the smaller the location of our maximum gets, right? So zoom in here real nice. So as A gets larger, the location of our maximum and the value of our maximum gets smaller, which makes sense because as A gets larger, 1 over A is going to get smaller. Well, so is 1 over AE. So we're able to confirm what we're seeing with Desmos.